Section 10.6, we're going to turn our attention to finding segment lengths in circles. So we've been working with angles and arc measures, and now we're going to turn our attention to actually finding lengths of segments. So the first deal here is we have to understand segments of a chord, okay? And so essentially when you have two chords that intersect in the interior of a circle, you'll notice that you actually create four different segments. So if I draw two chords in this circle, there's one, there's two, you'll notice there's four different chords here. Okay, you have the green one, you have the blue one, and then we obviously have another black one right here, and then we have the red one that's left. So again, when you have two chords that intersect, there are four segments that are created, and those are four segments that we'll be working with here today. A secant segment is a segment that contains a chord of a circle and has exactly one endpoint outside the circle. Okay, so in other words, something like this would be a secant segment because you have this portion of the segment is a chord, and then this smaller portion is outside the circle. So a secant segment is a segment where part of it is outside of the circle. And then finally, an external segment is the part of a secant segment that is outside the circle. All right, so again, the external segment here is going to be that little outside part right there, that secant segment. Okay, or we'll call it the outside segment too. All right, so the first theorem here simply states that if two chords intersect in the interior of a circle, then the product of the lengths of the segments of the chord is equal to the product of the lengths of the segments of the other chord. Okay, so what in the world does that mean? Well, if I look at this diagram, EA times EB has to be equal to EC times ED. Okay, more simply put, if you look in the diagram down here where I have my segments labeled A, B, C, and D, if I take A times B, that product has to be the same as C times D. No matter how long or short each chord is individually, those products will always be the same. Okay, so example number one here says find X, find ML, and find JK. So to find X, I have to just set this up. I have two chords that intersect, so I know that the product of each segments have to be equal. So 9 times X has to equal 3 times 12, so that's 9X is equal to 36. Divide both sides by 9, so X in this particular diagram has to be 4. Okay, so if X is 4, then it should make sense that JK equals 9 plus 4, which is 13. And ML is pretty simple. All you're going to do is add your 12 and your 3, so ML is 12 plus 3, which we all know is just 15. So again, pretty straightforward examples here as we look at this theorem for the first time. The second theorem says, now you'll notice when the two chords intersected, the angle was inside, and this is one where the angle is outside. But again, we're not talking about angles and arc measures now. We're going to be talking about lengths of segments. Okay, so if you have two secant segments that share the same endpoint outside the circle, then the product of the lengths of one secant segment and its external segment is the same as the product of the lengths of the other secant segment and its external segment. So the whole times outside is equal to whole times outside. So in other words, EA times EB is equal to EC times ED. All right, so outside times the whole thing, outside times the whole thing, outside times the whole thing. So when we look at this first guy up here in example 2 says find the value of X and RT. Okay, so again, I have two external secants. So I have, let's see, I take the outside times, now the whole thing here is not going to be 5X, it's X plus 5 equals outside times the whole thing is 10. And so you'll notice here I have to distribute this guy, so I get 5X plus 25 equals 60. Subtract your 25 from both sides. I'm going to come over here, so you get 5X is equal to 60 minus 25 is 35. Divide both sides by 5, X equals 7. Okay, if X is 7, then it's pretty obvious that RT has to be 7 plus 5, which is 12. Okay, this next example, example 3 here, kind of summarizes both of these ideas at one time here. So we have one example of each. So in this first part it says just find the value of x. So again, you have two chords that intersect. All right, and so we know that the product of x and 6 has to be the same as the product of 12 and 5. So 6x, 12 times 5 is 60. Divide both sides by 6. X in this particular diagram has to be 10. Alright, we're going to actually skip part B here because I just realized that the numbers that I gave you in that example are going to work out to be pretty ugly here. So we're not going to actually go through and do part B. Okay, but we'll talk more about that type of example in class tomorrow. Alright, and then the last theorem, the third and final theorem, says the segments of secant and tangent theorem. Okay, so in other words, when you look at this diagram, if you have one tangent line, or tangent segment, and then you have a secant segment, then the rule is the tangent segment squared, so EA squared is equal to, and that's the same thing that we've been doing, outside times the whole thing. Okay, and so that's the relationship here. So we have find x and RT. So again, we have the tangent segment squared equals the outside times the whole thing. Alright, so 14 squared, 14 times 14, I believe is 196, is equal to, distribute the 7, so you get 49 plus 7x, subtract your 49 from both sides, and so we end up at 7x equals, let's see here, we have 196 minus 49, which is 147, divide both sides by 7, x is going to equal 21. Alright, so x is 21, and since x is 21, that makes RT 7 plus 21, which is 28. Part B here, same idea. Okay, you have a tangent segment and you have a secant segment, so you have your tangent segment squared equals outside times the whole thing. So x squared equals 4 times 13 is 52. So x equals the square root of 52. And again, you could get a decimal equivalent if you want, but since that's not a perfect square, we don't have to worry too much about that. So again, this section is all designated to finding segment lengths. We've looked at finding arc measures and angle measures within circles, and now we're looking at finding lengths of segments. So again, as always, bring any questions you have to class. We'll take some of those to start the hour, and then we'll plug away with some more examples.